Translational equilibrium problems, we've done them in one dimension, and they work out fine. We've also done a lot of one-dimensional motion. When we jump from one dimension into two dimension for motion, we didn't really make big changes. We just said we're going to have vectors, we're going to have to break them into components, and then we're going to do the same exact thing we had been doing before. We're just going to kind of do it twice. With equilibrium problems, it really works like that too. So this is a video about a translational equilibrium example in 2D. Maybe I have a picture. It's a very nice portrait, and it's hanging up on a wall. But for whatever reason, this is, maybe it's a children's museum, and instead of hanging things by one very simple thing, we like to be just a little bit goofy and hang this from two chords. Maybe this picture has a mass of, we'll make it a heavy picture, it's going to be 4 kilograms, and we know that this rope hangs at an angle of 37 degrees with the vertical. I want to know what are the tensions in my ropes. Here we go. I'm going to draw my free body diagram, and in this case it's going to look very much like my original picture, but that's okay. I have an M1G, just an MG I suppose, pointing straight down. I've got a tension 1 that points over in this direction, and a tension 2 that points to the right. I'm going to say upward can be my y-axis. There's no motion, so it doesn't really matter what direction I pick, but I've got a vector that points straight down, a vector that points straight to the right. If I choose a regular set of axes like this, then those two vectors are already on just an x or just a y-axis, which is going to save me some work in the long run. So there's my free body diagram, and I'm going to just put in my angle because I think it's going to end up being a helpful thing to have. And that's it, really. My mass is 4 kilograms. So now I don't need my picture anymore. I am on to just using my diagram. I'm going to treat my x and y directions separately. Now this T2, this points just in the x direction, MG points just in the y direction, and that's great. Those are going to be easy. T1 has to be the difficult one. So I want to take T1 and break it into two components, one that points in the x direction and one that points in the y. So let me do that. I'm going to say this points up and to the left, so I will break it into a vector that points up and a vector that points to the left. This one over here, this is my T1y, this is my T1x, and those make a right angle. T1y is going to have a magnitude of T1 times cosine of the angle, because it's the adjacent side. T1x is going to have a magnitude of T1 sine theta. Now I'm going to start doing my sum of force equations. In the x direction, I have T2 goes to the right. Let me start like this. My sum of forces in the x direction are, I have T2 pointing to the right. I have T1x right here pointing to the left. And this is a static translational equilibrium problem. so that's going to equal 0. I can put in a little bit more detail because I know my T1x kind of. T2 minus T1 sine theta equals 0. Great, but I don't know T2 or T1, so this is an equation that has two unknowns. Now I'm going to look in my y direction, see what I can do there. In my y direction, I can look at my sum of forces, and I can say I have T1 cos theta, so T1y points upward, and I have mg points downward, and that equals 0. I'm going to put in, again, a little bit more detail. T1y is T1 times cosine of theta minus mg equals 0. I'm solving for T1, and it's my only unknown in here, so I'm going to add mg to both sides and get T1 cos theta equals mg, and then I'm going to divide by cos theta. That cancels it out over here, and I get T1 equals mg over cos theta. I'm going to plug in my values, so 4 kilograms, 10 meters per second squared, and then the cosine of theta, it's a 37-degree angle, so I will put divided by the cosine of 37 degrees. The cosine of 37 degrees happens to be equal to 0.8, or 4/5. So I get a value here. 4 times 10 is 40, over 4/5, so times 5/4 is 50. And there's my T1. I am halfway done with my problem. Now I need to find T2. I do have, conveniently, this equation up here that'll work really well as soon as I've got T1. So this equation says T2 minus, and now I'm going to put T1 in black because I know the value, T1 sine theta equals 0. I'm going to add my T1 sine theta to both sides. And I get T2 equals T1 sine theta. So it equals 50 newtons times the sine of 37 degrees. The sine of 37 degrees is 0.6. Or 3/5. So this is 30 newtons for T2. I found T1 and I found T2 both. T1 is bigger than T2 because it's the more vertical force and I only have the two forces going on. Another way to think of this, T1x right here, T1x has to cancel with T2 because those are the only x forces. If those two don't cancel with each other, if those are not balanced, then this picture is going to be swinging side to side, and I don't have that going on. T1, right here, the diagonal, is made up of T1x plus something extra. So if I've got T1x matching T2, and then T1 is that plus some more, then I expect that T1 is going to be bigger than T2. And it is. That's how you solve a problem with sometimes multiple unknowns. That's definitely how you solve a two-dimensional problem in static translational equilibrium. For the sake of organization, it might be a helpful thing to bring in one of our tables. So this problem is finished. Just be very clear, this problem's finished, but it might be a nice thing for you to be able to have this same thing with tables. I am effectively looking at this T1, T2, these are vectors, mg is a vector, and I'm saying, let me look at my x direction business and my y direction business. And in the end, my total force has to be 0 for x and has to be 0 for y. My mg was a 0 here, and a negative m times g, 4 kilograms times 10 meters per second squared is 40. My T2 is just T2 as an unknown and 0 in y. And my T1 is a T1 sine theta in the negative direction for x, and a T1 cos theta for y. And then it's the same problem that I just did. So if you like splitting up your vectors in a table sort of format, this will work out fine for you. If you would rather just say, I'm going to work in the x direction first, do what I can do there, then work in the y direction, do what I can do there, and put them together, that's completely fine too. They are just two different ways of organizing the exact same thoughts.